Good morning, good afternoon, or good evening to everyone, especially to Sir Zaifa Abdullah. So, I am going to discuss to you the aqueous solutions and chemical equilibria, the principles of neutralization, titration, and complex acid and base system. So, my name is Shara Fernandez Abdullah, your reporter. So these are the contents of my report, which is the aqueous solutions and chemical equilibria, principles of neutralization, titration, complex acid and base system. Most analytical techniques require the state of chemical equilibrium. At equilibrium, the rate of a forward process or reaction and that of the reverse process are equal. So the photo on the right shows, which is the photo on the books, the beautiful natural formation called Frozen Niagara in Mammoth Cave National Park in Kentucky. As water slowly seeps over the limestone surface of the cave, calcium carbonate dissolves in the water according to the chemical equilibrium. So this is I think the formula, which is the CaCO3. So nakita niyo naman sa baba. So, equilibrium is a state of balance. So, chemical equilibrium is a state of balance between the reactants and products. As reactants form products, some products form back the reactants. Reactions in which the reactants form products to completion are said to be irreversible, while reactions in which the reactants form products and the products can reform the reactants are said to be reversible. So, aqueous solution in which water is the solvent, or called aqueous solutions, example, sugar solution or sugar dissolved in water. Among the strong electrolytes listed are acids, bases, and salts. A salt is produced in the reaction of an acid with a base. So, example, yung NaCl, Na2SO4, and NaOOCCH3, which is the sodium acetate. So, ang acid and bases, according to Bronsted-Lowry theory, ang acid is a proton donor. So, and a base is a proton acceptor naman. For a molecule to behave as an acid, it must encounter a proton acceptor, or a base, or vice versa. While the conjugate acids and bases is a conjugate base is formed when an acid loses proton. So, mawawala yung proton. For example, acetate ion is the conjugate base of acetic acid. So, a conjugate acid is formed when a base accepts a proton. This is how acid and base act as a conjugate acid-base pair, or just a conjugate pair. Similarly, every base accepts a proton to produce a conjugate acid. So when these two processes are combined, the result is an acid-base or neutralization reaction. So this reaction proceeds to an extent that depends on the relative tendencies of the two bases to accept a proton, or the two acids to donate protons. So in an aqueous solution of ammonia, water can donate a proton and act as an acid with respect to the solute NH3. So makikita nyo naman yung NH3 plus H2O2 NH plus 4 plus OH negative. So yung ammonia, base 1, reacts with water, which is the acid 2, to give the conjugate acid ammonium ion acid 1 and hydroxide ion base 2 of the acid water. So on the other hand naman, water acts as a proton acceptor or base in an aqueous solution of nitrous acid. So as you can see, the H2O plus HNO2 to H3O plus NO negative 2. So the conjugate base of the acid HNO2 is nitrite ion. So the conjugate acid of water is the hydrated proton, written as H3O1, and this species is called the hydronium ion, and it consists of a proton covalently bonded to a single water molecule. So let's move on to autoprotolysis. So ang autoprotolysis is also called autoionization. So it is the spontaneous reaction of molecules of a substance to give a pair of ions. So the hydronium and hydroxide ion concentrations in pure water are only about 10 raised to the negative 7 m. So strengths of an acid and bases. So dissociation reactions and relative strengths of some common acids and their conjugate bases. So this is the strongest acid, the weakest acid, the weakest base, and strongest base. So the most common strong acids include yung hydrochloride, yung HBrH, IHClO4, HNO3, the first proton in H2SO4, and the organic sulfonic acid or RSO3. And the most common strong bases include the NaOH, KOH, Ba or AOH, and the quaternary ammonium hydroxide, where R is an alkyl group such as the CH3 or C2H5. So many reactions never result in complete conversion of reactants to products. So they proceed to a state of chemical equilibrium in which the ratio of the concentrations of reactants and products is constant. So ang equilibrium constant expressions are algebraic equations that describe the concentration relationships among reactants and the products at equilibrium. So ang equilibrium state naman is the final position of a chemical equilibrium is independent of the route to the equilibrium state. So the equilibrium constant expression becomes yung pang second na formula. So this is the equilibrium constant important in analytical chemistry, which is the types of equilibrium, the name and the symbol of equilibrium constant, the typical example, and also equilibrium constant expression. So makikita nyo naman lahat yung mga formula nila. So let's jump on to the example. So calculate the hydronium and hydroxide ion concentrations and the pH and pOH of 0.200 moles aqueous and AOH at 25 degrees Celsius. So this is how you calculate it. So sodium hydroxide is a strong electrolyte, and its contribution to the hydroxide ion concentrations in this solution is 0.200 mole or liter, as in example 9 to 1. Hydroxide ions and hydronium ions are formed in equal amounts from the dissociation of water. So therefore, we write it as the open and close parenthesis of OH and then negative sa taas is equal to 0.200 plus the open and close parenthesis of H3O plus. So where H3O plus is equal to the hydroxide ion concentration from the dissociation of water. So the concentration of OH negative from the water is insignificant. So however, compared with 0.200, we can write it as open and close parenthesis of negative and then yung 0.200. So POH is equal to negative log 0.200 is equal to 0.699. So after that, equation 911 is then used to calculate the hydronium ion concentration. So i-copy mo lang yung H3O plus and then equal to KW, sa baba niya is yung OH, which is yung 2 is 0.200, and then yung 1.00 times 10 to the power of negative 14 is constant na yan siya. So i-divide just at 0.200 and then equals to 5.00 times 10 to the power of negative 14 mole. So i-attach ko na lang yung mga picture dito. After mo times to divide, and then ang result is 0.500, and then i-negative log mo siya, and then ang lalabas is 13.301, pero dito sa calculator is 14.301. Then after that, note that the approximation, so i-copy yung OH negative and then ipag-plus mo lang yung 0.2 plus 5.0 raised to the negative to the power of negative 14. So ang magiging answer nyo is 0.200 m. We don't have the significant error in our answer. So let's move on to the next, which is the principles of neutralization titration. So, solutions and indicators for acid-base titration neutralization titrations are widely used to determine the amounts of acids and base and to monitor the progress of reactions that produce or consume hydrogen ion. So there are several different types of acid-base titration, which is the titrating strong acids with strong bases, titrating strong bases with strong acids, titrating weak acids, and with strong bases, titrating weak bases with strong acids. So titrating a strong acid with a strong base, we will be interested here in calculating hypothetical titration curves of pH versus volume of titrant. Three types of calculation must be done to construct the hypothetical titration curve for titrating a solution of a strong acid. So each calculation corresponds to a distinct stage in the titration: the pre-equivalence, equivalence, and post-equivalence. So in pre-equivalence stage, we compute the concentration of the acid from its starting concentration and the amount of base that has been added, and then in equivalence point, the hydronium and hydroxide ions are present in equal concentrations, and the hydronium ion concentration is derived directly from the ion product constant for water. In the post-equivalence naman stage, the analytical concentration of the excess base is computed, and the hydroxide ion concentration is assumed to be equal to or multiple of the analytical concentration. So, in solutions and indicators for acid-base titrations, neutralization titrations depend on chemical reaction of the analyte with the standard reagent. So, there are several different types of acid-base titration. Number one is the titration of a strong acid such as the hydrochloric or sulfuric acid with a strong base such as sodium hydroxide. The titration of a weak acid such as the acetic or lactic acid with a strong base. And then the titration of a weak base such as the sodium cyanide or sodium salicylate with a strong acid. So in standard solutions, reagents used in acid-base titrations are always strong acids or strong bases, as I always saying. So in weak acids naman, bases are never used as a standard reagents because they react incompletely with analytes. Standard solutions of acids are prepared by diluting concentrated hydrochloric, perchloric, or sulfuric acid, and then yung nitric acid is seldom used because its oxidizing properties offer the potential for undesirable side reactions, and then the hot concentrated perchloric and sulfuric acids are potent oxidizing reagents and are very hazardous. So in acid-base indicator naman, an acid-base indicator is a weak organic acid or a weak organic base whose undissociated form differs in color from its conjugate base or conjugate acid form. So the undissociated form of the indicator has a color different from the color of its ionized. So these substances change their color according to variation of pH or the potential of hydrogen of medium. Another is the titration errors with acid-base indicators, and then titration of strong acid bases, tapos converting hydroxide contrast pH can be developed by taking the negative logarithm of both sides of ion product constant expression of. Those are the things na mapagdadaanan before calculate yung principle of neutralization titrations. Let us now jump into the examples para mas madali niyong maintindihan. So my problem is in a titration of hydrochloric acid with barium hydroxide of 32.00 ml of 0.150 m HCl is required to neutralize 26.75 ml of the barium hydroxide solution. So calculate the molarity of the hydroxide solution. So remember, you must work in liters per volume since you are performing mole calculation using units of molarity, which are moles. So here are the solution. So first thing to do is to list the known values, write the balanced chemical equation, and plan the problem. Known to unknown. Molarity of the HCl solution, volume of the HCl, volume of the, until sa baba. Multiplication and division lang ang ginamit ko. So therefore, our final answer is 0.0897 moles. So this is the complex acid-base system. So let's jump into the next, which is the examples para mas madali. So this is the example I chose, which is the 3 of 13. which is the carbon dioxide and carbonic acid system. So here, calculate the pH of a solution that is 0.02500 and CO2. So the equation here is CO2 is equal to 0.02500 is equal to CO2, and then hanggang sa baba na siya. So that's how you calculate it. Then the charge balance equation is the open and close parenthesis of H3O plus is equal to HCO3 negative plus 2CO3 2 negative close parenthesis plus OH negative. So then assume that 2 is CO3 2 negative plus OH negative to HCO3 negative. Substituting these approximations in equation 13 of 6 leads to, so as you can see, the open and close parenthesis of H3O plus raised to negative 2 divided 0.02500 is equal to Ka1 is equal to 4.2 times 10 negative 7. So here sa baba, copy the H3O plus na open and close parenthesis is equal to yung square root of 0.02500 times 4.2 times 10 raised to negative 7 is equal to, I will attach here the calculations I did para magtugma sila. So the answer is 1.02 times 10 raised to negative 4. And then yung mole. Tapos, pH is equal to negative log 1.2 times 10 raised to the negative 4. I-attach ko na lang din yung final answer nyo, which is 3.99. Final answer is 3.99. So, calculating values for H2CO3 and CO3 2 negative and OH negative indicates that the assumptions were valid. So that would be all. Thank you for listening.